Good day, students. In this clip, we're going to be going over some examples that will help you review how to generate graphs of rational functions. So let us take a look at question number 1, where to determine the equation of any vertical asymptotes and the values of x for any holes in the graph. Okay, so how do you find the holes in vertical asymptotes? We're going to start out by writing down the procedure for finding each. So to find the holes, you set factors that cancel out, to 0, and then solve. So if you have a rational function, you factor the numerator and the denominator. Any factor that's common in the numerator and denominator that you can cancel out are the equations that you use to solve for the holes. Okay. All right. So let's talk about the vertical asymptotes. How do you find the vertical asymptote? To find the vertical asymptote, you're gonna set denominator factors. Set denominator factors. Set denominator factors that do not cancel out. Set those ones equal to 0 and solve. Okay, so the ones that cancel out tell you your holes, and the ones that do not cancel out tell you your vertical asymptotes. Just for your information, holes are also known as your removable discontinuities. All right, and vertical asymptotes are also known as your poles or infinite discontinuities. All right, so let's go ahead and find the holes first. So to determine what the holes are, we have to determine what factors cancel out. Okay, so write down the numerator and the denominator. Now, what does the numerator and the denominator have in common? In order to answer that, we have to factor out the denominator. Okay, so let's use the AC method here. AC is 10 and B is -7. Two numbers that work here are -5 and -2. We do not need to factor by grouping here because A is 1. Alright, so this is equal to x minus 5 divided by x minus 5 times x minus 2. Now examine this function. What do you notice? You notice that x minus 5 is common in the numerator and the denominator, so it can be cancelled out. So x minus 5 goes here 1, x minus 5 goes here 1. So whichever factor cancels out, that tells you your holes. Alright, so to find the holes, we're going to set the factor that cancels out equal to 0 and solve. You add 5 to both sides and you have x equals 5. There goes your hole. And then to find the vertical asymptote, all you do is you look at the denominator and extract factors that did not get cancelled out. Okay, the reduced form of the polynomial expression, you just set the denominator of that polynomial to 0. So in this case, x minus 2 doesn't have any common factor in the numerator, so we just extract it. Set it equal to 0 and solve. X equals 2 is our vertical asymptote. All right, so let's see, where's the answer? Holes 5. So it cannot be A or B. Vertical asymptote of 2, so our answer is option letter C. All right, let's take a look at question number 2. We have a transformed rational function here, f of x equals -7 over x minus 6, and we're asked to sketch the graph of the resulting transformed function. Now we'll take a look at the standard parent function for rational functions. F of x is equal to 1 over x. There are some interesting things that we can determine from this function. First of all, we can clearly see that the vertical asymptote is going to be 0, so let me create my coordinate system here. So let's see, coordinate system, there goes my x-axis and my y-axis. Now for the parent rational function f of x equals y 1 over x, the vertical asymptote is equal to 0 because you set the denominator x equals to 0, right? And then it's already solved. Nothing cancels out here, so the only factor in the denominator that remains is x equals 0. So we have a vertical asymptote right on the y-axis, so you have a vertical asymptote right here. And then in this function, you also have a horizontal asymptote of 0. You have that because it is bottom heavy, and at infinity or negative infinity, this whole expression collapses to 0. So you have another asymptote here, or horizontal asymptote. Alright? Now, the nature of this graph is as follows. From the left side, you start from the asymptote, and your horizontal asymptote, and head towards negative infinity. And then on the right side, you start from infinity and head towards your horizontal asymptote. All right, so it's good to memorize the way this function looks like. All right, this is the orientation of the parent function. Now if you look at this equation, this is a transformation of this. You notice this negativity means that this function is simply reflected along the x-axis. So if you want to have f of x equals negative x, it's negative 1 over x, it's going to have this appearance with each portion reflected to the opposite, to the coordinate above or below. So this one goes up here to there, and then this portion right here goes to here. This negative reflection does not have any impact on the asymptotes, all right? Now how about this 7 right here? This 7 basically means a dilation along the y-axis. It just stretches it up or down vertically. So that doesn't have significant impact on the look of the graph. But this x minus 6 is important. This x minus 6 is a shift along the x-axis, all right? So since x minus 6, we're going to do the opposite. That means you're going to shift 6 units to the right. So f of x equals negative 7 over x minus 6 is a dilation of a factor of 7 along the y-axis and a shift of 6 units to the right. So it's going to look something like this. So let's say you shifted it 6 units to the right. Let's say this is 2, 4, 6. So you shifted 6 units to the right, then your vertical asymptote will also move along with that. It will be shifted 6 units to the right. Your horizontal asymptote remain unchanged since there is no translation in the vertical direction. All right. Now your function that's being reflected and dilated by a factor of 7 is going to look something like this. Remember, the dilation is not that significant. It doesn't significantly alter the appearance in the sketch. This is not perfect. It's just a sketch. So this is what your graph should look like. All right. Okay, so let's take a look at this right here. If you wanted to do it in a different way, you can solve for the solve for the vertical asymptote. How do you solve for the vertical asymptote here? What you do is you set the denominator equal to 0, and you solve, and you have x equals positive 6. So you go down to positive 6, 1, 2, 3, 4, 5, 6, and you draw your vertical asymptote. All right? And then you look at this function and you say, oh, it's bottom heavy, so you know that your horizontal asymptote is going to be 0, because any bottom heavy rational function has a horizontal asymptote of 0. All right? And then ideally, a rational function of this nature will look something like this. You have one here and another here. I'm sorry, you have one down here and then another here, but with this minus, it gets reflected. So instead of having a portion of it down here, you have a portion of it up here. As you approach this vertical asymptote, you tend towards infinity, and then down here, you start from negative infinity and head towards your horizontal asymptote like that. And you can definitely verify the accuracy of your graph, of your sketch, by using a calculator. A TI-89 or any graphing utility should suffice. So I'm going to input this function into my graphing window and then see if it matches what I have here. So negative 7 divided by, now since we have two terms in the denominator, we have to group it with parentheses, okay? So x minus 6. Close that, enter. All right, let's graph it. Diamond F3 is the graphing for TI-89 titanium. Let's see. And then over there. All right, you can see that at 1, 2, 3, 4, 5, 6, we have a vertical asymptote. So this shows that our answer is in fact correct. All right, so there you have it. But thanks so much for taking the time to watch this tutorial. Feel free to subscribe to our channel. We really appreciate it. More clips can be found on mathgotserved.com. And also post a comment to let us know what you think about this clip. Thanks again for watching and have a wonderful day.